Welcome to this explainer. Let's dive right in. We interact with large language models every single day, right? But how often do we actually stop to look at what physically happens to our words inside the black box? Today, we're getting into the deep details. We're going to trace the exact journey of a single prompt from its smallest granular unit all the way to its macroscopic effect on an AI model's architecture. We are going to unpack exactly how these systems process information and, more importantly, why they sometimes fail completely.
Because, we've all been there. You build a perfect retrieval system, you give the AI the exact documents, the exact answer is literally right there in the text, and it still confidently gives you the wrong output. To figure out why this happens, we really have to look under the hood at the mechanical bottlenecks of large language models. It's not magic, it's a sequence of mathematical operations. And those operations, they have some pretty serious vulnerabilities.
So, Section 1, Anatomy of an AI Input and Tokenization. Our journey really starts at the very beginning of the pipeline with the microscopic parsing of your text. Let's look at how the model actually reads. Before a model can even try to answer a question or summarize a document, it has to break your text down into segments it can mathematically understand. We call these tokens. Now, don't think of tokens as letters. Think of them as kind of like arbitrary puzzle pieces, usually mapped out using algorithms like byte-pair encoding. But here is the absolute critical part. Because this mapping happens before the model even sees anything, the AI completely lacks native morphological awareness of individual letters. It literally only operates on token-sized units, which fundamentally explains why these massively intelligent models still mess up basic spelling, character counting, or simple math. They quite literally do not see the letters the way you and I do. And this disconnect is perfectly illustrated right here. Take the word unhappiness. Now, a human naturally splits this into its root and affixes, right? Unhappiness. That preserves the meaning. But an LLM tokenizer, it doesn't care about meaning at this stage. It only cares about statistical frequency based on its fixed vocabulary limits. So it might just arbitrarily chop the natural word into un, ap, and innis. That random segmentation subtly and sometimes drastically shifts the model's baseline understanding of your input. And if you want quantifiable proof, it's pretty striking. Looking at a study from TCS Research, we can actually see how this tokenization penalty affects performance. Across multiple NLP datasets, they found a super clear correlation. When an LLM, like Phi 3.5 in this case, is forced to process natural words that have been chopped up into these weird subtokens, its accuracy just fundamentally degrades. The model actually performs significantly better when words map cleanly to single tokens. So the big takeaway here is that tokenization is absolutely not just some harmless prep step. It introduces severe representation errors. All those arbitrary splits accumulate, causing this massive morphological disruption across your prompt. And worse, if the model gets hit with glitch tokens, rare sequences outside its main training data, it completely breaks the model's attention mechanism. This penalty hits before the AI even starts processing your core instructions. It's handicapped from the get-go. All right, Section 2, System versus User Prompts. Moving to the next layer, let's see how this builds into the actual structural boundaries of the prompt itself. Once the text is tokenized, how does the model actually know what to prioritize? When you use an API, your inputs are segmented into a really strict hierarchy. On one side, you have the system prompt. You can think of this as the persistent job description for the AI. It sets the rules, the role, the behavioral boundaries. Then on the other side, you have the user prompt. This one is super dynamic. It's transient, basically acting like a task sitting in an inbox. It's just the specific query for that exact moment. And the way the model processes this hierarchy is just fascinating. It always processes that system prompt first. This primes its attention mechanisms and literally shifts its probability distributions to favor certain vocabularies and constraints. Only after that does it even look at the user prompt. This dual attention setup is absolutely crucial because it treats those system instructions as a higher authority. It's a built-in architectural defense to keep the AI from forgetting its core identity just because a user tries to trick it into doing something contradictory. Moving into Section 3, Lost in the Middle. Because even if we perfectly tokenize our input and brilliantly architect our system roles, we hit a massive working memory bottleneck once data floods into the context window. This is a hugely famous phenomenon known as lost in the middle. Now, you might be using a model that brags about a massive 128,000 token context window, which is basically the length of a whole novel. But just because it has the space doesn't mean the model uses it all equally.
Research from Stanford, Berkeley, and others proves these models have a severe positional attention bias. They hyper-prioritize whatever is at the very beginning and the very end of your prompt, but they have a massive blind spot for anything buried in the middle. It's literally the AI equivalent of middle child syndrome.
Just look at this U-shaped accuracy curve. If you put a critical document at the start of your prompt, boom, accuracy is sky high. Put it at the very end, same thing, high accuracy. But if you drop that exact same document right in the middle, the model's retrieval accuracy just completely falls off a cliff. What this means in practice is that the maximum effective context window of a model is way, way smaller than its advertised size. Those middle tokens get proportionally less mathematical attention, and your vital data just decays. So to prevent your context from rotting in that middle dead zone, you've got to engineer it. You can't just blindly string retrieved documents together in a random order. You have to intentionally reorder them. You want your absolute best, most relevant chunk placed right at the beginning and your second best chunk placed at the very end. You also need to aggressively limit your context size. Keep it to maybe 4 to 8 highly relevant chunks. Filter out the distractors, because adding more context actually ruins performance if it pushes the vital stuff into the middle. Okay, section 4, the in-context learning secret. We've got our context perfectly positioned, so let's hit the deepest part of the machine to see how the AI actually learns from it. We all know LLMs have this incredible ability to learn new tasks just by looking at a few examples in a prompt, completely without any permanent retraining. This is called in-context learning. For a long time, it was a bit of a mystery, and we honestly thought it was mostly just pattern matching. But deep research, like a massive paper by Dye and colleagues, revealed something wild. It is actually a form of implicit fine-tuning where the language model secretly acts as a meta-optimizer.
Here's the deep detail on how this works under the hood. When you drop demonstration examples into your prompt, the AI uses forward computation to generate what researchers call metagradients. It takes these metagradients and applies them to its own attention vectors on the fly. Basically, it's building a temporary, highly specialized version of itself right in that moment just to answer your specific query, all without making any permanent parameter updates to its underlying neural weights.
When you look at this side by side, the math is actually super clear. Explicit fine-tuning and in-context learning, they share the exact same mathematical dual geometry. They rely on the exact same training information and causal order. The only real difference is how they execute it. Fine-tuning uses backpropagation for permanent parameter changes, while in-context learning uses forward computation for temporary attention shifts. The AI is literally actively fine-tuning itself in real time inside your prompt. Which brings us to section 5, mastering the AI architecture. Let's zoom back out for a second and apply this deep mathematical reality to our daily interaction with these systems. How do we take all of this and actually build better applications? Now that we know how fixed tokenizers can just shatter natural words, how that middle dead zone inherently rots data, and how the model uses forward computation to implicitly fine-tune itself on the fly, we absolutely have to change our approach. We have to stop blindly dumping data into massive context windows and just hoping the AI will figure it out. As this quote nails perfectly, the real fix is rigorous context engineering. You have to select certified context, rank it, place it intentionally, and compress it if you want to survive these architectural bottlenecks. And that leaves us with a pretty fascinating final thought to wrap up this explainer. If we know that current transformer architectures are essentially just real-time meta-optimizers that are heavily choking on subword token limits and positional memory decay, what does the next evolutionary leap in AI actually look like? Will future models finally ditch the crutch of tokenization and read character by character? Will they somehow conquer the lost in the middle bias to unlock truly infinite context? Understanding exactly how the black box is broken today is really the only way we can prepare for whatever comes next. Thanks for joining me on this deep dive into the data.